On eastbound regional train number 148 to Spring.
Attention customers, please be advised. The first and last car of all trains traveling to North End Station.
Hello students, this is the first time I'm actually doing a lecture at a train station, but this is a lecture. It should be short because I got through most of it. So I was asked several times by email why the powers are important. And the reason the powers are important is because, if you recall this example, I needed to know what alpha squared was so that I could substitute all the other multiples as I expanded out this Cayley table. So in general, if you're going to build the Cayley table for a 25 by 25 set of members of a group, or a ring, you would have to know what those powers were. And that's why it's important to raise the powers. So again, right here, recall that I have reduced alpha squared to a linear factor. In the same way, you're reducing alpha to the fourth to a cubic factor, and so forth, so that you can express all of your elements in terms of the first few elements here. So alpha squared by itself is not a new element. It turns out alpha squared is really alpha plus 1. So this is why, and I hope it's clear. So moving forward, just to remind you, we have homomorphisms and normal groups, and we also know that the kernel of the homomorphism is a normal group in G, and we also know that we can formulate a factor group H. So we would like to have an analog of normal subgroups for rings. The goal is to fill this in, and I'm not going to fill it in all the way yet because it's just a bit much, but the analog of a normal group for rings is called an ideal. The definition of an ideal is kind of like the definition for a normal group. I is a subset of the ring, where R is the ring. I is a two-sided ideal, or we just say ideal if 1, I is a subgroup under plus, and 2, that we have some kind of normal-like property under times. And you see this x times r belongs to I, and r times x belongs to I. And this is for all x in I and for all r in R. It's a very similar definition to normal groups. What these two pieces mean, the 2 and 3, is that it kind of sucks in, I sucks in all the products. So, I anticipated having this in class, but what if I have that 1 belongs to the ideal? Well, if 1 belongs to the ideal, and all products in R belong to 1 times R, then belongs to the ideal for all R, and it turns out that the ideal is R. So whenever if there is a multiplicative identity belongs to the ideal, the entire ideal is equal to R. I would ask you to prove that 0 and R are always ideals by themselves, so that just having 0, the additive identity, and just having R will always be ideal and satisfy the definition. What we want, just like the analog of normal subgroups, we would like the kernel to follow suit, and we do have that. The kernel of phi, where phi is a ring homomorphism, is going to be an ideal.
Please stand back from the yellow
I will
line
prove
and
this.
please watch the
What do I need to show?
the train.
Well, I need to show that if x belongs to I, which is the kernel, and R belongs to R, then x times R is I. And I also have to show that R times x is I. So if I write down the definitions, x belonging to I means that x belongs to the kernel, and it means that there's an f of x is equal to the 0. What do I need to show? I need to show that if x belongs to I, okay, so next up I copied and pasted, sorry. But if R belongs to R, then I know that phi of x times R is phi of x times phi of R by the the homomorphism property, and that's 0 times phi of R, but 0 times anything is 0, which is a property of the 0 of a ring, which you can prove actually. That means x times R also belongs to the kernel of phi. The same argument will show R times x belongs to the kernel of phi, and I think you can see that. Finally, this is an abelian group under plus, because if I have x and y belong to I, then phi of x and phi of y are 0. But v of x plus v of y is v of x plus y, which is 0. So what that means is x plus y remains in the kernel, and so we have closure under addition, and I is going to be an increase under plus. Of course, you don't really, I didn't really need to prove this, we have this already. What if R is a field? If I have a field, the only ideals are 0 and F. Think about why.
There's something you know. There's nothing in it.
If B is a ring homomorph and I have x belongs to R, the property that x has to have a multiplicative inverse means that phi of x is not 0. I can see this because if I assume on the contrary that phi of x is 0, then I get phi of x times x inverse, which is phi of 1, is 0. But phi of x is 0 implies that phi of 1 would be 0. But a property of homomorphisms between fields tells us that phi of 1 has to be 1. So that's a contradiction, because that would imply that 1 has to equal 0, which is impossible. So I'm not going to collect this homework, but finish the rest of the proof, and we will continue ideals, not next Monday, next Monday, and then we have the test on Wednesday. Oh, actually I have to check the survey, so I'll check the surveys and send you the update.